Welcome to the 13th lecture on ECD. We will continue studying FET amplifiers and the high frequency of FET amplifiers. In fact, in the last lecture, the 12th lecture, we studied the upper cutoff frequency for an FET amplifier, that was a common source amplifier, due to the input RC network. And this was the expression that we derived in this lecture. The expression includes Rs, that is the source resistance that is by default with the AC voltage source. This one. So this is the Rs. And the value of this resistance is very small, few hundred ohms, or even sometimes lesser than 100 ohms. And times C in total, or C total in. C in total is the gate to source capacitance. This is the junction capacitance. This one, the junction capacitance between gate and source terminals, plus the voltage gain plus 1 times CGD. CGD is the capacitance that is between the drain and the gate, between the output and the input terminals. So we have to divide this CGD into two parts. One is solely on the output side and the other is on the input side. So we used Miller's equation to divide it into two parts, and the part that is visible on the input side by applying Miller's theorem is this one, 1 plus AB times CGD. So what we are going to do in this lecture is we are going to find out the same upper cutoff frequency, but this time it is due to the output RC network instead of the input RC network. So let's see how to find FC, the upper cutoff frequency, due to the output RC network, and then we'll compare the two values. Right. So this is the output circuit that we see. This is the output circuit that we see at the output, and we know that this FET amplifier is a voltage controlled amplifier. Therefore, the equivalent circuit can be drawn like this. Like what? Like this. This is the dependent current source whose value is dependent on the input voltage VGS. What this source says is this RD in parallel with RL, and in parallel this coupling capacitor is bypassed in parallel with C out total, and the output is computed across this capacitor. This is our load. So this equivalent circuit, we studied circuits like this in, it's a recap from the last course, EDC, Electronic Devices and Circuits course. This is a recap from the last course, EDC. So what we have to do is, right, in order to convert, we can apply source transformation here. Source transformation here to convert this current source in parallel with this combination of resistors to convert it to a voltage source, and this resistor comes in series. So source transformation, we studied source transformation in the course linear circuit analysis. It's also a recap from LCA, the first course on circuit analysis. So we can convert it into a voltage source, and that voltage source would be GMVGS times RD in parallel with RL, and the same resistor is no more in parallel, but it is in series now. So it is in series now. So now we have this RC network, and we know that at the cutoff frequency for this network, for this RC network, XC of this capacitor, C out total, is the same as RD in parallel with RL, this resistor. So we know that at cutoff frequency, this impedance or capacitive reactance is the same as the resistance in series. Therefore, we have already studied that FCU can be written as 1 over 2 pi RD in parallel with RL times C out total. C out total. So this is what the upper cutoff frequency for an FET network, or an FET amplifier, and amplifier is common source amplifier. Right. So now let's solve a numerical problem by considering the circuit that we solved in our last lecture, ECD12. So in ECD12, we solved a problem, an example. So the problem was this RD was 1K, RL is 10M, and CGT is 3 picofarad. We have taken this problem from the last lecture, ECD12. And GM, the transconductance was 6,500 microsiemens. So this is the data available, and what we have to do is we have to find this upper cutoff frequency by putting values in this expression. Right, we know RD 1K, RL 10 meg, and we know that C total on the output side is 1 plus AV over AV into CGT. So this is the expression found out by Miller. So this is Miller division of CGT on the output side, and part of it is also available on input side that we studied in last lecture. So this is the part of Miller available, or the part that is there on the output side. Right, so now we know CGT, but the only unknown is AV now. So if we somehow know AV, we can plug these values in this expression and can find FCU. So computing AV is simple. We know AV for an FET amplifier, common source FET amplifier is this. We studied that in EDC course. GM times RD in parallel with RL. So plugging these values in GM, RD, 1K, RL, 10 meg. It comes out to be 65. So let's plug this value in here. AV 65 here. CGT is 3 pico. And then plug C out here. RD 1K, RL 1 meg. Solving everything gives FCU output. FCU due to output coupling capacitor it comes out to be 46 megahertz. Whereas a recap from the last lecture, ECD12 tells us that FCU we computed using input. Our C network was 116 megahertz. So now we can finally draw a body plot. Where this is the midband and this is the first cutoff frequency, and of course lower will be the significant or dominant cutoff frequency, this one, and the fall here would be minus 20 dBs per decade, and here it is minus 40 dBs per decade. So this is this and this is this, right? That's all for this lecture. Thank you.